Hello everyone, my name is Varsha Pinumali and I am an incoming senior at Troy High School. There is a large amount of publicly available time series gene expression data present today due to the availability of microarrays and transcriptome high throughput sequencing. For a given disease under the same control conditions, it is expected that the meta-analysis of different datasets allow researchers to identify patterns in publicly available data that are previously unexplored. Time series high throughput gene expression profiles hold significance in numerous applications. Some of these applications include identifying responsiveness to drugs, genetic interactions, and tumorigenesis. For applications specific to personalized medicine and drug repurposing, it is even more crucial for healthcare professionals and researchers to have easy access to this information and relevant articles as they rely on gene expression levels based on genetic differences. However, current literature retrieval methods result in a large number of false positives. As a result, one must manually read through a plethora of articles before a meta-analysis can be performed. In our case, a manual query regarding rat retina injury with the RATS mesh term on PubMed returns 2,224 articles. The criteria used to determine usability includes topic pertinence, variability, meaning duplicates, temporal information, genes, and relevant pathways, only 63 of which fit the criteria through manual curation. That is over 97% of false positives. For this reason, it is extremely time prohibitive to complete a meta-analysis of time series gene expression data without automated text mining. To make this information more accessible to healthcare professionals and researchers, we have devised an algorithm for automatic literature retrieval with 3 key steps. First, identifying the article. Second, extracting the pathways from the abstract. And third, extracting the pathways from the table. Now I will hand it off to Lei to discuss how the algorithm was created and its results.
Thank you, Varsha. Hello, everybody. My name is Lei, and I will be talking about the prototype in more detail. Out of these 63 articles identified using mesh terms, we are only working with the 56 articles that are fully available on PubMed Central. We begin by extracting gene symbols from the abstracts. For this purpose, the PubData Central database is accessed using the PubMed Minar package. For articles where no genes can be found in the abstract, we instead rely on the tables of these articles to find this information. By using tidyPMC, tables for an article can be accessed by using the XML version of this article. The genes can then be extracted in the corresponding column. Once a list of genes has been retrieved for all the articles, we explore the associated pathways by performing an enrichment analysis using gProfiler. The top 44% of the returned pathways were selected based on the lowest p-values. For the articles that return no results, we pass the genes through KEGREST, which returns all the pathways associated with a certain gene. Pathways identified by gProfiler were found to be a lot more accurate than KEGREST when reconciling the results against manually curated pathways. This is expected because KEGREST simply returned a comprehensive list of pathways which were associated with all the given genes. Despite its higher inaccuracy, this method allows for the articles which had too few genes for the pathway enrichment analysis to remain useful. In the end, 84% of the articles had information on genes and pathways we could fetch programmatically. The next step is to further reduce false positive on pathways returned, and incorporate text mining to verify that an article of interest has temporal data and retrieve it for meta-analysis. That concludes our presentation. Thank you for listening.